All right, hey everybody, my name's Ricky and I'll be leading you through this exercise today, and we're going to be going over magnetic force and how it acts on to a particle. So before we dive into it, I just want to give kind of an applied example of something that's actually utilized frequently here, which is when you go to the airport and you go through TSA, sometimes they will get like a Q-tip or some kind of swab and put it over your hands or all over your luggage and then put it in something called a mass spectrometer. And so what happens there is there's some like particulates that comes off from swabbing that, then they put it in the spectrometer and then they like vaporize it, with some magic. Well, I don't know, they have something, but they vaporize it, and then if something gets singly charged, singly ionized, they then it's accelerated through an electric field, and then it's acted upon on a magnetic field, and then there's some gyration that happens due to this positively charged particle and it being acted on an electric field, and then through that they're then able to figure out the mass of what this element is, and then once you know the mass of what this element is, they're able to deduce if it's a good thing or a bad thing, basically. That's kind of to my general understanding of how that process works. And so that's like a real life example on something of value to know this process. So to get things going, this program we have is very similar to one you've done prior, where we had a particle just be accelerated by the electric field as drawn right here. This is step one. You just looking at this here. This is very similarly written as that previous exercise, but we have yet to put in the effects of the magnetic field acting onto the particle. We do see it gets accelerated by the electric field as we expected, and if you've been following the videos, as you saw in the particle acceleration exercises. And then step two is you just open the code up, and if you do have an account, make sure to log in and then make a duplicate of this, and then I'll just run it here just so you can see that we haven't yet plugged it in, and it comes in, gets accelerated, and then something's supposed to happen as it comes into the magnetic field, but that we have yet to introduce that. So we know that the force is equal to Q times V cross B, and so there's two different right-hand rules, and I'll go through both of them. And these are important tools that I still use to this day, because qualitatively it lets you know what you need to know. And in this case, we just want to know which direction is our particle moving. So let me get a better frame here. So one thing to know is that the force should be perpendicular to the velocity and also to the direction of the magnetic field. And so with that in mind, we know that our particle is moving in this direction here, and with our magnetic field this way into the page. And so the only way for our force to be perpendicular to both of these directions is it's either force got to be going up or it's got to be going down. And so now we're just deducing which one is it. And so now let's get to the right-hand rule, which will help decide that for us. And so you just do your pointer finger, just try to line it up with the particle here in the direction of its velocity, and then we do our remaining fingers into the page, like just showing you, but you can't see, into the page. Let me go right here, and then our thumb that's remaining is letting us know that, okay, of the direction either up or down, it must be going up. And so that's what that means. Our V cross B value is positive, and now we multiply it by Q, which is also positive. Thus, we know that the direction of our force that should be acting onto our particle will be in the positive Y direction or in the up direction. Now for the other right-hand rule, very similar, is our middle finger in the direction of the velocity, and then the magnetic field is into the page. You know, each boom, it's like your palm of your hand is into the page, so we're good. And then it needs to go up. So our V cross V value is positive, needs to go up, and then the charge is also positive, so stays up. So same, both of these rules work. Kind of depends, you know, if you want your hands like this, or you know, if you do this way, you know, you kind of get the fun, like, woo, let's go, we did it, you know, right hand rule. So, you know, I do it to this day. So that's kind of qualitatively, now we do know what we should expect when we're coding this up and actually putting in values. You'll see that the force in the positive y direction will lead to a motion for the particle like this, roughly. Step 5 is just to help the understanding of the force of the magnetic field coming on to acting onto our particle. And so in general, the net force in the x direction is just the summation of the forces in the x direction, and in this case it's just the force of the magnetic field. In this case is the only thing acting on our particle, so it'd be the force of the magnetic field in the x direction. And then it always holds true thanks to Newton's second law, thanks to him, but also due to Newton's second law, it's equal to mass times acceleration in the x direction. And similarly is said for y, where the force of the magnetic field in the y direction is equal to the mass times the acceleration in the y direction. And here's our formula that we just discussed a moment ago of QV cross B. And so in general, we talk about the magnitude of this force in the magnetic field, and that leads to a result that we know commonly as QVB. But that implies there's no directionality on this force, but there is, right? Because we just showed it with the right hand rule. And so to kind of break that down some more of each of the force that is felt in each direction, we have it defined right here, where the force in the x direction due to the magnetic field onto our particle is QVYB, and then in the y direction is minus QVXB. And so here we have it just kind of to prove to you that this does lead to the result that we expect. We define it out here, but something that you might be wondering is, why is there a negative sign here? What's that about? So now let's just visually, more qualitatively begin to understand on why that minus sign exists in front of our QVXB. And so just looking here at our plot, we have our coordinate system defined here. And so we know our particle is moving in the positive x direction. Our magnetic field is moving in the negative z direction, so there's a negative sign in front of our magnetic field, our variable b, and we know the charge of the particle is positive. And so if we go back down to our formula and we look at the force in the y direction, and let's ignore this negative sign for now. Let's just say it's QVXB. And we know that we're expecting, given our right hand rule, we're expecting it goes up, meaning it's a positive value. And so let's ignore this minus sign here, and let's just plug in, you know, if they're positive or negative, right? So Q is positive, Vx is positive, and B is negative. And so ignoring this minus sign, right, this doesn't exist, it's just QVB, that would lead to the outcome of a negative value at the end, thus saying that the force in the y direction should be down. But we know due to the right hand rule it shouldn't be, so it should be going up. Thus that's the reasoning behind why we need to have a minus sign here. Now in step 6, now we're actually going to go into the code and kind of begin plugging in the values necessary to actually show the impact of the magnetic field acting onto our positively charged particle. So the first thing to do, though, however, is to solve for what the acceleration is to these forces. And so we know that for the force in the x direction, it's q vy b naught, and then for in the y direction, it's negative q vx b naught. And earlier also, we know that these forces are equal to the mass times acceleration in the x direction and the mass times acceleration in the y direction. So you set these values equal to each other, and then you solve for the acceleration, you solve for A. So now let's go to our code and we'll put that in. We're going to write these in, but to make things a little clearer, we're going to define variables for the force in the x direction and for the force in the y direction. And so here we get f of x is equal to q. And if you need to know what it is, you can refer back to the exercise page, but I know it's Vy times the magnetic field B. And then I can't forget semicolons, then Fy is equal to Q times, can't forget the minus sign, times Vx times B. Alright, so now that we got that written out, now we can, like I said, the force is equal to mass times acceleration. I already discussed that earlier, but then you just divide over the mass to solve for what that is. But we'll go ahead and write this in here. We'll get the force F of x divided by the mass times r delta t. And then similarly, in the y direction, we'll get f of y divided by the, oh, actually, it's not m in the code, it's actually written out as mass times delta t. Alright, and then if this works correctly, we should be able to run this and something cool, oh, I'm in the way, should happen. Boom. Physics right there, real time. And we write out what the final velocity in the x and the y direction should be, or what our program calculated. Alright, now the gyro radius. You saw that in the motion it had, it looked like a perfect like semicircle almost. And that radius of that circular path is called the gyro radius. And so we want to know what this gyro radius is. And we have the initial, or we have all the values necessary to figure out what that gyro radius is. Let's just go back. Let's just refer to this one here. This is the same as the code that I did. And so we have so we start here in some initial position y, it's 250, and its final position ends at 434.3. And so this, if we subtract those values together, we'll get the diameter of this circle, of this circle, and then to get the radius, we would then divide it by 2. And so let me whip out my handy Desmos. So we have 434.3 minus 250, and then that's the diameter of our sphere. And so gotta make sure you want the radius, and we get 92.15 as our gyro radius. Here we go. And then now we'll move to the glass board for this, but we'll work on finding a formula to then actually calculate the true and expected value of what this gyro radius should be, using things that we learned a little bit if you had watched the video of Project Mercury, where the acceleration of this circular path goes as a v squared over r, which is the gyro radius, and we can use that and solve for it. This will be done on the glass board, which will be a different video, but that's what we go through in this part 7b, and then we'll compare them. And what you'll see in that is to get good agreement, somewhere between 10%, and when you go back and refer to that video, you'll see we'll get somewhere around, I think it was around like 3.5%. Which is really good. It's a pretty solid agreement, and it's really important to always go back and do what the actual true value would be, because computers can be wrong. We could have, we could mistake in the positive side, we could have messed up and put a value in. So it's always good to mathematically go back and use the equations that we know to actually try to find a relationship to see what the true value would be, and then see if there's good agreement between the code that you made, that we just made here in this video, that it's in good agreement with the expected value.